Welcome back to the Sleepless Scientist Channel. This is the little corner of YouTube where science is not rushed, not overwhelming, not noisy. Here, we slow down, we breathe, we let the mysteries of the universe unfold at their own gentle pace. And tonight, we're going to ask a question so simple, so childlike, that it almost feels like a riddle whispered in the dark. Does space ever end? It's the kind of question you might ask as a kid, staring up at the stars. And maybe an adult would smile and brush it aside. But the truth is, it's not silly at all. It's one of the biggest questions science has ever faced. The more we think about it, the larger it grows. The edges of our imagination stretch wider and wider. And suddenly, we're not asking a child's question anymore. We're asking a cosmic one. So tonight, I'd like to take you on a journey. Not a fast journey, not a dramatic one, but a slow drift outward, through physics, through time, through the vast ocean of space. Along the way, we'll visit Newton's clockwork universe, Einstein's curved fabric of space-time, the quantum buzz that fills even the emptiest vacuum, and the faint afterglow of the Big Bang. By the time we're done, you might be asleep, or you might still be awake, staring at the ceiling, lost in thought. Either way, I hope you'll feel calmer, smaller, but in the best possible way. Because sometimes, realizing how vast the universe is can make our worries shrink down into perspective. Before we set off, may I ask a small favor? If this kind of content brings you comfort, please consider subscribing. It helps keep this sleepy little channel alive, and I'd love for you to be part of our community. Also, let me know where you're watching from and what time it is right now. Maybe you're tucked into a warm bed in London at 11:30 p.m. Maybe you're at a desk in Toronto at 3 inches the afternoon, pretending to work. Or maybe you're lying in a hammock somewhere tropical, listening to the waves as you drift with the stars. Reading your comments always reminds me how beautifully scattered this community island. Like galaxies across the cosmos, we are spread out everywhere, and yet connected by the same night sky. So now, get comfortable. Adjust your pillow. Loosen your shoulders. You don't need to learn or memorize. You don't need to focus. Just let the words wash over you like starlight on calm water. And just a gentle reminder, this video is meant for relaxation and curiosity only. It is not medical advice, nor a replacement for professional treatment. If you're ready, take a deep breath, let it go, and join me as we begin this slow, quiet journey into the question, does space ever end? So, what exactly is space? When we look up at the night sky, it feels like a giant black canvas, dots of stars sprinkled across an endless backdrop. To most of us, it feels like nothing, a void, an emptiness that simply holds everything else. For centuries, that was the way people thought about it. Just a background, a stage on which the real actors, planets, moons, stars, play out their roles. This was the picture Sir Isaac Newton gave us. To him, space was absolute, fixed, unchanging, a vast stage, stretching forever in every direction, and time ticked forward the same way for everyone. It was solid, it was reliable, it was the cosmic theatre. But then, along came Albert Einstein, and with him, a revolution in how we see reality. Einstein told us that space is not passive at all. It's not just an empty box that sits there forever. Instead, space is flexible, dynamic, alive. According to his general theory of relativity, space and time are woven together into a single fabric, a fabric that bends and curves whenever mass and energy are present. This fabric is called space-time. To picture it, imagine a trampoline. Stretch a rubber sheet tight. That sheet is space-time. Now place a heavy bowling ball in the middle. The sheet dips. The fabric curves. If you roll a marble across the surface, it won't move in a straight line. It curves around the bowling ball, not because the ball is pulling it with invisible strings, but because the sheet itself is curved. That, Einstein said, is how gravity works. Not as a mysterious force that pulls objects toward each other, but as the bending of space-time itself. You don't fall toward the Earth because it tugs on you like a magnet. You fall because Earth bends the space-time around it. And you are simply rolling along the curves. This was a radical shift. Suddenly, space was no longer just an empty backdrop. It was an active player in the drama of the universe. It could bend. It could ripple. It could even expand. And when you put this together with the strange rules of quantum mechanics, you discover something even more surprising. Space is not empty at all. Now, you might be wondering, if space can bend and curve around stars and planets, then what happens when there's nothing in it at all? What about the vast, silent gaps between galaxies? What about the lonely stretches of darkness far away from every star? Surely that must be true emptiness. Surely that must be nothing. But it isn't. Thanks to quantum mechanics, we now know that empty space is never truly empty. At scales far smaller than atoms, smaller than protons, neutrons, or even quarks, space itself trembles with activity. Physicists call these invisible layers quantum fields. And here's the strange part. These fields aren't inside space. They are space. Every particle in the universe is born from its own field. Electrons spring from the electron field. Photons come from the electromagnetic field. Quarks emerge from their quark fields. Even if no particles are present, the fields never rest. They flicker, they shift, they ripple with hidden energy. And sometimes, for the briefest instant, this energy creates tiny particles. They appear, exist for a heartbeat, and then vanish again, like sparks in the night, like fireflies blinking in and out of existence. This restless background is called vacuum energy. Imagine standing at the edge of a still pond. From far away, the water looks perfectly smooth. But when you kneel down and look closely, you notice tiny ripples, swirling currents, the sudden leap of a fish breaking the surface. It only looked calm from a distance. In truth, it was never still at all. That's how the vacuum of space works. What appears silent and featureless is actually alive with motion. Physicists have even detected the effects of these invisible fluctuations. They change how electrons behave inside atoms. They may even be tied to the mysterious force we call dark energy, which seems to push the universe apart faster and faster. So, space is not nothing. It is not an empty box waiting to be filled. It is an active, restless sea, a place where particles flicker in and out, where energy hums softly, always present, even in the deepest voids. And the strangest truth of all? This restless vacuum is not just alive with motion, it can also stretch. Not just the galaxies moving farther apart, but space itself, expanding beneath them. Here's where things become even stranger, because space is not just something that can bend or ripple, it can actually expand. Not just the stars drifting apart, not just galaxies flying away from each other, but the very fabric of the universe itself stretching beneath them. This idea comes straight out of Einstein's theories, and it sits at the heart of modern cosmology. To picture it, let's return to that trampoline or rubber sheet. Imagine once again the bowling ball in the middle, curving the fabric. Now imagine that the sheet itself is being stretched wider and wider. Every point on the sheet moves away from every other point. That is what's happening to the universe. The galaxies are not racing through space like cars on a highway. They are being carried farther apart because the road itself is stretching. This is the expansion of space. At first, this idea can feel overwhelming, because we naturally think of space as something fixed, something eternal. But Einstein's work showed us that even the emptiness between galaxies is dynamic. It grows, it stretches, it changes over time. And there is a strange comfort in this thought, because it means the universe is not a dead, static void. It is alive with motion, humming with energy, expanding in every direction. Even in its quietest corners, space is never still. It is like the soft crackle of a fireplace or the rustle of leaves in the night, always moving, always changing. So when we ask, what is space? We are not talking about nothing. We are talking about a living fabric, one that can bend, ripple, and expand. And with this discovery came another startling realization. If space is expanding, then there must be a limit to how far we can see. A cosmic bubble that defines our horizon. A boundary, set not by walls, but by time itself. If space is always expanding, then we quickly run into a very natural question. How far can we actually see? Stand outside on a clear night, and it feels like the stars stretch on forever. The darkness above looks endless, eternal. But in truth, there is a limit, a boundary to our cosmic vision. We call it the observable universe. It is not a wall. It is not the edge of all that exists. It is simply the farthest distance light has had time to travel since the beginning of everything. Think of it like a bubble. We are at the center, not because Earth is special, but because every observer, no matter where they are, sees their own bubble of the observable universe. You might think the radius of that bubble should be about 13.8 billion light years, since that's the age of the universe. After all, light has been travelling for 13.8 billion years, so shouldn't that be the farthest we can see? But the universe has a trick, because space itself has been expanding while the light was on its journey, and this expansion has stretched the distances far beyond what simple math would suggest. Today, the radius of the observable universe is about 46.5 billion light years, which means, from one side to the other, our cosmic bubble spans nearly 93 billion light years across. Think about that for a moment. The universe is only 13.8 billion years old. Yet, we can see galaxies that are more than 3 times farther away than that. It is like watching someone walking toward you on a treadmill that is stretching beneath them. The path between you keeps growing even as they move closer. By the time they arrive, they have crossed a distance far longer than the treadmill's original length. This is how light behaves in an expanding universe. It has been stretched, pulled, and carried along by the growth of space itself. So, our observable universe is not the whole story. It is just the part of the cosmos we can see. Beyond that bubble lies something. Maybe infinitely more galaxies. Maybe whole regions of space we will never touch. The boundary is not a physical wall. It is a horizon made of time and light. And beyond that horizon, the mystery continues. The observable universe gives us a bubble of what we can see. But there is another boundary, one even more haunting. It is called the cosmic horizon. Unlike a physical edge, this horizon is not a wall. It is more like a fading fog. Beyond it, light simply has not had enough time to reach us. And so, no matter how powerful our telescopes become, those regions remain invisible. But there is an even stranger twist. Because space is expanding, and the expansion is accelerating, some galaxies are receding from us faster than the speed of light. Not because they are breaking Einstein's rules, but because the space between us is stretching too quickly. The result? Any light they emit today will never reach us. Not in billions of years. Not in trillions of years. Not ever. We can still see some of those galaxies right now. We see the ancient light they sent long ago, when they were much closer. But as time passes, their newer light falls behind, caught in the river of expansion that carries them away forever. It is as if you are standing on a shore, watching lanterns float down a river. For a while, you see their glow, but eventually, the current sweeps them beyond the bend, and they vanish from sight. In the same way, galaxies we see today will someday drift beyond our horizon, visible now, but destined to fade away. Not because they burn out, not because they disappear, but because their light will no longer reach us. This means that the universe we see now is temporary, a fleeting snapshot of a much larger, ever-changing reality. Pause for a moment and look up at the night sky. Every star you see, every faint smudge of galaxy, all of them lie safely within our horizon. But beyond that, the universe continues, silent, unknown, forever out of reach. It is a humbling thought. We are witnesses to only a fraction of the cosmos, a small glowing bubble in an ocean without end. When we look into the night sky, it feels as though we are seeing the universe as it is right now. But that is an illusion. In truth, every star, every planet, every galaxy we see, we are seeing them as they were, because light takes time to travel. And in the cosmos, those travel times can be immense. A light year is the distance light travels in a single year, about 6 trillion miles, or nearly 10 trillion kilometers. When you look at a star 100 light years away, you are seeing it as it was 100 years ago, when your great-grandparents were young. When we look at a galaxy millions of light years away, we see it as it was millions of years ago. And when we peer at the most distant galaxies of all, we are gazing billions of years into the past. to an era long before Earth even existed. Some of the light entering your eyes tonight began its journey before the first oceans formed, before the first single-celled life appeared, before our solar system was even born. This is what astronomers call look-back time. The farther away an object is, the older the light we receive. A galaxy 8 billion light-years away has a look-back time of 8 billion years. We are not seeing it as it is today. We are seeing a fossil image of its ancient past. And here is a strange truth. Some galaxies we observe may no longer exist. They may have collided with others. They may have burned out their stars. They may already lie forever beyond our cosmic horizon. But we still see them, frozen in time, because their ancient photons are only now completing their journey. In this way, light is not just illumination. It is a messenger, a time capsule, a cosmic record of history written across the stars. When you gaze upward at night, you are not only looking into distance, you are looking directly into the past. Every twinkle is a story from long ago. Every glimmer is a chapter of the universe's history. The night sky is not a view of the present. It is a window into memory, the universe showing us what it once was. If every glance into the night sky is really a glance into the past, then telescopes are our time machines. A small backyard telescope might let you see the moons of Jupiter, or the rings of Saturn, or perhaps a bright nebula glowing a few thousand light-years away. Already, you are looking into history. But larger telescopes, resting on mountaintops or orbiting above the Earth, let us travel much deeper in time. With them, we can see galaxies so far away that their light began its journey hundreds of millions of years ago, back when life on Earth still swam with fins and crawled with gills. And then, there are the giants, the great observatories, like the Hubble Space Telescope, which for decades has shown us dazzling images of far-off galaxies, nebulae, and star clusters, and now, its successor, the James Webb Space Telescope. James Webb is so powerful, it can collect the faintest whispers of ancient light. It can peer across billions of light-years, reaching back to the first stars and galaxies that formed only a few 100 million years after the Big Bang. When we see those galaxies, we are not seeing them as they are now. We are witnessing their youth, the first flickers of light in a newborn universe. It is a paradox of astronomy. To learn about the future of the cosmos, we must spend our time looking into its past. Light travels fast, but space is unimaginably vast. And so, by the time ancient photons reach us, they carry with them a story already billions of years old. It is like watching a movie that is always delayed. Scenes from different chapters arrive together, some from nearby stars just a few years away, others from galaxies billions of years distant. Piece by piece, astronomers stitch these scenes together, like gathering scattered pages of a history book, written in the language of light. The result is a patchwork of cosmic memory, a record of how galaxies grew, how stars ignited, and how the universe itself unfolded from fire into form. So when we point a telescope at the sky, we are not just looking outward, we are reaching backward. We are holding in our hands a machine built for time travel, and in its mirror, we see the faint glow of beginnings. So far, we've talked about the observable universe, the bubble of space we can see, defined by how long light has had time to travel. But there are other horizons in cosmology, other boundaries that shape what we can and cannot ever know. The first is called the particle horizon. This is the maximum distance light could have traveled to us. Since the moment of the Big Bang, it marks the outer edge of our observable bubble, not because there's a wall, but because light beyond that distance hasn't had enough time to arrive. Imagine standing in a wide, foggy field. You can see a certain distance in every direction, but beyond that, everything fades to grey. Not because nothing exists out there, but because your eyes can't pierce the fog. That's what the particle horizon is like. Now, the second horizon is more subtle. It is called the event horizon. Don't confuse it with the kind around a black hole, though the idea is similar. In cosmology, the event horizon is the boundary beyond which events can never influence us, no matter how long we wait. Why? Because space is expanding so quickly that light from beyond this horizon will never overcome the distance. It is like standing by a river and tossing a bottle upstream. The current is too strong. No matter how hard you throw, the bottle is swept away. Likewise, there are galaxies we can see today. Their ancient light has reached us, but any new light they send will never arrive. They are already slipping away, carried faster than light by the stretching fabric of space. Finally, there is the cosmological horizon. This is a more general idea. It refers to the shifting boundary of what can be observed, depending on how the universe evolves. Some horizons expand as time passes, others shrink, as dark energy pushes galaxies out of reach. The result is a bittersweet truth. As the universe ages, our observable bubble becomes lonelier. More and more galaxies fade beyond the horizon, never to be seen again. We live in a universe with limits. No matter how powerful our instruments become, there will always be regions hidden from us. Not because of clouds, not because of walls, but because of the very nature of spacetime itself. And in that mystery lies both humility and wonder. We are small, our vision finite, our horizons real. But within those horizons lies a universe already vast beyond comprehension. A universe filled with enough beauty and strangeness to last us a lifetime of discovery. For a long time, people thought the universe was steady, eternal, unchanging. The stars seemed fixed in place. The heavens looked like a calm and endless stage. It was comforting to imagine that the cosmos simply was. But in the early 20th century, that picture shattered. A man named Edwin Hubble peered into the night sky with one of the most powerful telescopes of his time. What he saw changed everything. The light from distant galaxies was shifted toward red, stretched as if the wavelengths themselves had been pulled longer. This phenomenon, called redshift, meant those galaxies were moving away from us. And not only that, the farther away they were, the faster they seemed to be receding. This was no coincidence. It was a law of nature. The universe was not static. It was expanding, not like stars flying through empty space, but like space itself stretching underneath them. To picture this, imagine a loaf of raisin bread rising in the oven. The dough is space. The raisins are galaxies. As the dough expands, every raisin drifts away from every other raisin. Not because the raisins are moving on their own, but because the dough itself is growing. And here's the curious part. There is no center raisin. Every raisin sees the others moving away. Every observer, no matter where they sit, believes they are at the center of expansion. This is how the real universe works. It is not expanding into something else. It is expanding everywhere, all at once. When Einstein first wrote down his equations, he assumed the universe must be static. To force that result, he added a cosmological constant that acted like a cosmic glue. Later, when Hubble's discovery proved expansion was real, Einstein called that constant his greatest blunder. Ironically, the idea of the cosmological constant returned decades later to explain the acceleration of the universe, what we now call dark energy. The universe, it seems, has a sense of humor. But Hubble's discovery gave us more than irony. It gave us a way to rewind the cosmic clock. If everything is expanding outward now, then long ago, everything must have been closer together. Much closer. This leads us back to the idea of the Big Bang. Not an explosion in space, but the rapid expansion of space itself. Everywhere. All at once. From a hot, dense beginning, the universe stretched and cooled, forming stars, galaxies, and eventually, us. Even today, nearly 14 billion years later, the expansion continues. Galaxies drift apart, light stretches into red, and the story of the universe keeps unfolding. In physics, there is one rule that seems absolute. Nothing can travel faster than light. Not a rocket ship, not a beam of sound, not even a thought experiment. Einstein's relativity places the speed of light as the ultimate cosmic speed limit. And yet, we look out into the universe and see galaxies receding from us faster than light itself. How can this be? Is the universe breaking its own laws? The answer lies in a subtle truth. Those galaxies are not racing through space. They are being carried apart because the space between them is stretching. Relativity forbids objects from moving through space. faster than light, but it says nothing about how quickly. Space itself can expand, and space can expand very, very fast. To picture this, imagine dots on a balloon as it inflates. The dots don't move across the surface. Instead, the surface itself grows, carrying every dot away from the others. Or, think of yourself walking on a treadmill. If the treadmill moves backward faster than you walk forward, you never make progress. That's what happens to light in an expanding universe. Nowhere is this more dramatic than in the universe's earliest moments. In the first fraction of a second after the Big Bang, something extraordinary happened. A burst of expansion called cosmic inflation. In less than a trillionth of a second, the universe grew from smaller than a proton to the size of a grapefruit, or perhaps even larger. This inflation happened faster than the speed of light, not because anything broke the rules, but because spacetime itself swelled at a staggering rate. Why does this matter? Because inflation smoothed out the newborn universe. It stretched tiny quantum fluctuations into the seeds of galaxies. It spread matter and energy almost evenly across the cosmos. That's why, when we look at the universe today, it appears remarkably uniform, the same in every direction, like the surface of an orange, dimpled here and there, but round and even overall. Even now, billions of years later, the fingerprints of inflation remain. We see them in the faint ripples of the cosmic microwave background, and we feel them in the loneliness of the night sky as distant galaxies drift beyond our reach forever. The lesson is humbling. Light may be the fastest traveller in the universe, but even light can be outpaced, not by motion, but by the restless expansion of space itself. When we imagine the universe, it's tempting to picture it like a giant box, a vast container with edges, corners, and walls. But space does not need to follow those rules. Its shape is more subtle, more mysterious. Einstein's equations tell us that the geometry of space is determined by how much matter and energy it contains, and that geometry, in turn, decides how the universe expands, and perhaps even how it will end. There are three main possibilities. The first is a flat universe. Picture an infinite sheet of paper. Here, the rules of geometry are just like you learned in school. Parallel lines never meet. Triangles always add up to 180 degrees. If you set off in a straight line, you will never come back. You just keep going, forever. The second is a closed universe, curved inward like the surface of a sphere. In this model, if you travel far enough in one direction, you eventually return to where you started. Like flying around the Earth, no edges, no falling off, just endless looping. The third is an open universe, curved outward like a saddle. Here, parallel lines diverge. Triangles add up to less than 180 degrees, and if you keep travelling straight, you will never return. You drift endlessly apart. So, which one do we live in? The answer depends on something called the critical density. If the universe contains more matter and energy than that value, it curves inward and is closed. If it contains less, it curves outward and is open. And if it matches the critical density exactly, the universe is flat. The Goldilocks option. Not too much, not too little, just right. For decades, cosmologists have searched for the answer, and they found their best clues in the faint afterglow of the Big Bang, the cosmic microwave background. By studying its ripples and patterns, scientists discovered that our universe is astonishingly close to flat. So close that if there is curvature, it is too small for us to measure. It's a bit like standing in the middle of a massive plain. To your eyes, it looks perfectly flat in every direction, and even if it curves gently somewhere far beyond the horizon, you would never notice. Still, the question lingers. Flat does not necessarily mean infinite. A space can be finite, and yet still have no edge, and that possibility leads us to something even stranger. A universe that is finite but unbounded. There is something deeply human about the idea of an edge. All around us, everything has limits. A table has edges. A book has covers. A road has a beginning and an end. So, when we think of the universe, it feels natural to imagine it must stop somewhere too. Surely, After enough distance, there must be an outside. Surely, there must be an end. But here is the strange and beautiful truth. Space does not need an edge. It can be finite in size, and yet have no boundaries at all. To imagine this, think about the surface of the Earth. From where you stand, the ground looks flat and endless. But we know the Earth curves back on itself. If you set off walking in a straight line, you will never fall off the edge. Instead, after a very long journey, you eventually come back to where you began. The surface of Earth is finite, but unbounded. Now, imagine this not in 2 dimensions, but in 3. A space that curves back on itself, where travelling forever in one direction might someday return you to your starting point. No walls, no edges, no outside. This is what cosmologists mean by a finite but unbounded universe. One way to picture it is with a torus, a donut shape. On the surface of a donut, you can wander endlessly without ever finding an edge. Left or right, up or down, the space just loops back on itself. Another way is through old video games. In Pac-Man, when you exit on the left side of the screen, you reappear on the right. Go off the top, and you come back from the bottom. The space is finite, but there are no borders. Some theories suggest our universe might work the same way. If so, then light travelling in a straight line could someday loop around and return from behind. A cosmic boomerang. If that were true, we might someday see repeating patterns in the sky, galaxies mirrored, like wallpaper printed across the heavens. So far, no such repetitions have been found. The universe may be too vast, or its shape may be different altogether, but the idea remains possible, and it reminds us that space is not like a box sitting inside a larger room. It does not need an outside to exist. It can be self-contained, complete, curved back upon itself. A universe with no edge, a cosmos with no border, a melody that loops forever, with no final note. Long before there were stars, before there were galaxies, before even the first atoms had fully formed, there was light. Not the sharp light of suns, but a soft glowing fog that filled the young universe. For the first 380,000 years after the Big Bang, the cosmos was too hot and too dense for light to travel freely. Photons, tiny particles of light, were trapped, bouncing endlessly from particle to particle, like prisoners in a crowded room. But then, as the universe cooled, protons and electrons combined to form neutral atoms, and suddenly the fog lifted. Light was free to move, and that ancient light has been travelling ever since. We can still see it today. It surrounds us, arriving from every direction in the sky. Stretched by billions of years of expansion, it now glows faintly as microwaves. We call it the cosmic microwave background. It is the oldest light we will ever see, a fossil from the moment the universe became transparent. In the 1,960 seconds, 2 scientists, Arno Penzias and Robert Wilson, accidentally detected it as a mysterious hiss in their radio antenna. At first, they thought it was static. They even blamed pigeons nesting inside the equipment. But no amount of cleaning made it go away. The hiss was not noise. It was the voice of the universe itself. The afterglow of the Big Bang, still echoing across the cosmos. Since then, satellites have mapped this ancient light in incredible detail. They found tiny ripples in its glow, the fingerprints of the first structures in the universe. From those ripples grew galaxies, stars, planets, and us. It is humbling to realize every breath you take is happening inside that ancient light. You are a ripple in its story. So, does space ever end? We don't know. It might be infinite. It might curve back on itself. It might be stranger than anything we can yet imagine. But maybe the answer isn't the most important part. Maybe what matters is the mystery itself, the wonder that keeps us looking upward, the humility of knowing we are part of something vast. When you lie down tonight and close your